So thank you very much for the brief introduction. So now moving on to the main presentation, the seismic behavior of concrete columns reinforced with hybrid reinforcement, steel and glass fiber reinforced polymer. So going through this presentation, I will talk about give a brief introduction on the problems of the corrosion in civil structures, like mainly in the North American countries where we have harsh environment from the winter. And I will little bit talk about the fiber reinforced polymer, its design philosophy, and how it is emerging nowadays. And I will give an overview of the fiber reinforced polymer bars. And finally, I will talk about my graduation project at the University of the Sherbrooke. So the corrosion of the reinforcing steel is the major cause of deterioration in concrete structure, and the alkaline environment of concrete, which has pH value of 12 to 13, provides a protective layer against the corrosion of the steel. However, the presence of chloride ions in de-icing salts and seawater reaches the steel reinforcement through minor cracks, and with the availability of moistures, chloride ions exceed the threshold limit and can induce rusting of the reinforcing steel. And this rusting causes expansion of the steel reinforcing bar and creates tensile stresses in concrete, which leads to cracking, delamination, and finally swelling of the concrete cover. So there is a loss of serviceability, and the concrete structure will require maintenance earlier than expected. So these are some of the examples we can see from the different highway bridges and parking building where we can see the corrosion of the steel bars or steel reinforcement. So in North American countries, there are available design codes and guidelines for concrete structure reinforced with fiber reinforced polymer. But there is a problem with that. There are insufficient experimental evidences on the behavior of fiber reinforced polymer reinforced concrete columns subjected to seismic loading. So therefore, they are not well documented in the design codes. The current FRP design codes and guidelines such as ASTO is used for the transportation, and Canadian Highway Bridge Design Code doesn't have sufficient provisions for the fiber reinforced polymer reinforced concrete column subjected to seismic loads. So why should we select fiber reinforced polymer bars? The fiber reinforced polymers bar can be considered in reinforced concrete columns due to the following characteristics. Fiber reinforced polymer bars have resistance against moisture, alkali effect, and chemical attack, which mostly depend on the selection of appropriate type of resin and manufacturing process and application of protective coatings. Therefore, the glass fiber reinforced polymer bars have resistance against deterioration due to chloride ions and carbonation. And also the fiber reinforced polymers are lightweight, non-conductive, and magnetic free, which is easy for the transportation, and it also reduces the labor cost. The fiber reinforced polymer bar are made from the composite materials, fiberglasses and carbon fiber, and is manufactured by a pultrusion process using a mix of recycled fibers and resin. And you can see from this figure, it shows a microscopic view of the fiber reinforced polymer bar, where we can see the fibers and resin and their interfaces. And generally, the fiber content is more than 80% of the total volume. So there are different types of fiber reinforced polymer bar available in the market. Those are carbon, aramite, glass, and basalt. And the stress strain plot shows how these fiber reinforced polymer bars are compared with the steel bar. So from this graph, 2 points should be noted. The glass fiber reinforced polymer bar have lower strength compared to the other two fiber reinforced polymer bars. And the second, the strength of all the bars are greater than the steel bar. But the problem here is the behavior of the fiber reinforced polymer bar is linearly elastic until the failure. So before moving on, we need to understand how the design philosophy of the fiber reinforced polymer bar, design of the fiber reinforced polymer reinforced concrete structure is different from the steel reinforced structures. So there are three different design philosophy, as you know that. One is the over reinforced section and balance section, and the under reinforced section. So generally the over reinforced section where is the concrete is the governing, and the under reinforced section is where the steel is governing in case of the steel reinforced concrete structure. So generally the steel reinforced concrete structure follow under reinforced section where the failure occurred due to the steel failure. So generally, because in this case, I have written FRP, but consider it as a steel. So in steel, where we first fill the steel, which provide ductility to the structure. And if we follow this thing, and as we know that the fiber reinforced polymer is linearly elastic up to the failure. Okay, so what will happen? The structure will have fiber reinforced polymer rupture first. So when it rupture first, the structure will behave like fail in a brittle manner. So we never want our structure to fail in a brittle manner during earthquake loading, right? So therefore, to avoid this kind of situation, the over reinforced section where we fail the concrete first is chosen for the fiber reinforced polymer concrete structure. So the assumption made in the design of the fiber reinforced polymer reinforced concrete structure, which are according to the American code ACI 440 and Canadian code CSA S806R. The plane section remains plane before and after the loading, so which means the strain developed in the concrete is proportional to the strain developed in the FRP bar. So this is similar to what we have learned for the steel reinforced concrete structure. So the assumed maximum allowable concrete strain is around 3000 microstrain, which is according to the ACI, and 3500 microstrain according to the CSA S806. The tensile strength or the rupture strength of the concrete is very low, so that's why it is ignored in the design. So the tensile behavior of the fiber reinforced polymer is linearly elastic and until the failure, and a perfect bond exists between the concrete and the fiber reinforced polymer bar. So the important question is where should we consider FRP bars? So as I told you, the FRP bars are good in corrosions. They can provide a better resistance against the corrosions. Those are lightweight, non-conductive, and magnetic free. So we can use it for any structure which are susceptible to the corrosion by chlorides and or chemicals. Any concrete structure requiring non-ferrous reinforcement due to electromagnetic consideration like MRI room. And as a cost-effective alternative to epoxy-coated or galvanized steel bars, and as a first cost saving over the stainless steel reinforcing bar. And for reinforced concrete members in tunnel and mining, where the presence of the moisture is more in the earth. And for this, nowadays, I think there are many projects which are using the FRP bars in the tunnel and mining section. They called it as a FRP rock bolt, or you can also call anchor bolt. These are also used in India also, because I was talking to one of the student from India, and he was telling that nowadays they are using FRP bars for the as an anchor bolt when they are doing the tunneling for the metro. And also for the structure where we require thermal non-conductivity, and in mass concrete exposed to marine chlorides near the chloride exposure, and we can use this also using the hybrid application like the steel bars. So in this figure, I'm showing it was a recent project in 2019 in Miami, where they use GFRP, glass fiber reinforced polymer FRP bar for piles. They constructed a sea wall using these GFRP walls throughout near the Miami Sea Beach. Now, moving on to my graduation project, the primary objective was to study the behavior of the concrete column reinforced with glass fiber reinforced polymer bars subjected to quasi-static cyclic load, and in terms of its composite behavior, failure modes, deformability, and overall stiffness. So I selected a full-scale test specimen which represent a ground floor which was cut at a mid height, and in order to fail in flexural mode, the selected cross section was around 400 by 400 with overall height of 1850 and with effective height of 1650 millimeter. The column was supported by a stub of 1200 by 1200 millimeter, and it was a height of 600 millimeter. So a total of 8 reinforced concrete columns, solely reinforced with glass fiber reinforced polymers bar, were casted, and each of the column was reinforced with 12 number of longitudinal bars. So the study parameters were the longitudinal reinforcement ratio, transverse reinforcement size, and the spacing of the transverse reinforcement. So the longitudinal reinforcement ratio consists of 12 number of 5 GFRP bar equivalent to 1.5% longitudinal reinforcement ratio, and 12 number 6 GFRP bar equivalent to 2.1% longitudinal reinforcement ratio. So 3 different sizes of GFRP spiral and cross tie were selected based on the North American code, and the spacing of the transverse reinforcement was generally based on the 1/4 of the minimum bar dimension, 6 times diameter of the smallest longitudinal bar, and 150 millimeter. The ready-mix normal weight concrete with a target concrete compressive strength after 28 days, 30 megapixel for the columns and 50 megapixel for the stuff were used, and the concrete compressive strength were determined by testing 3 standard cylinder that was of the size of 100 by 200 millimeter standard cylinder prior to the day of the column test. So this, whatever the strength we are getting from the concrete, it was used to give the constant compressive load to the columns during the test. So in case of the GFRP reinforcement, we use sand-coated grade 3 high modulus GFRP reinforcement conforming to CSA S807. And here I would like to mention that the GFRP bars generally comes in 3 grades. So with grade 1 refer to the low elastic modulus of the glass fiber reinforced polymer bar, and the grade 3 refer to the high elastic modulus. So in this case, because we are testing for the seismic loads, so that's why we use here the grade 3 GFRP bars. The elastic modulus was approximately around 60 gigapascal, and because of this is the grade 3, and therefore if you select the grade 1, those have like 40 gigapascal elastic modulus. I think this is similar to GFRP sheets or fibers what you use, and the tensile strength was around 2.1%. And these figures shows the GFRP bar, the cross ties, and the GFRP spirals used in the study. So to cover the most damaged region at 3 different locations, strain gauges and LVDTs were placed, and at 3 different level, 50 millimeter, 650, 350, and 650 millimeter above the column stem interface. The strain gauges of the GFRP spiral and two on the cross tie, and the strain gauges were installed also below the column stub interface here at 150 millimeter below and 350 millimeter below. And to understand the curvature of the column, 3 LVDTs were used at 50, 350, and 100, 400, and 700 millimeter above the column stub interface. So the column was tested in an upright position, and the column was attached to the laboratory strong floor by using 2 steel beams and 4 dividing bars. Dividing bars are the high strength steel bars. So the axial load was applied using 2 hydraulic jacks, which was attached to the steel beams at the top of the column, and the top steel beam was connected to the bottom steel beam using the 2 dividing bars, which was hinged at the bottom, as you can see here, using the spherical nut head to allow the free rotation of these 2 high strength steel bars. The MTS actuator was attached to the column tip using 2 high strength plates and 6 high strength rods, and the other end was attached to the laboratory reaction valve. So here you can see the concrete column during the experimental testing. So once the axial load reached 20% of the gross cross-section area of the column and concrete compressive strength, and it was maintained constant, And to reverse lateral cycle as shown was applied at 0.25% drift at an increment of 1%, then 0.5% drift increment till 3%, and afterward 1% increment until the failure of the column. So coming to the general what we observed during the experimental program, the initial distress in the column was due to the formation of these horizontal flexural cracks or the tension cracks, which was developed at a distance equal to the spacing of the transverse reinforcement. So further application of the lateral drift caused the corner concrete to split vertically, and which was earlier in the column with high spacing of the transverse reinforcement, like in the column with 150 millimeter spacing of the transverse reinforcement. It was occurring at a 1.3% drift, whereas with 100 millimeter, it was occurring at 1.6% drift. So this was followed by the spalling of the concrete cover in the similar manner what we observed earlier, like it was earlier in case of the column with the high spacing of the transverse reinforcement. So the failure of the GFRP reinforced concrete column was due to the first rupture of the sorry. Okay, so due to the first rupture of the longitudinal GFRP bars with the loss of lateral load, and also as you can see there is a loss of the lateral load, also the constant. This parts also the failure of the GFRP bars, longitudinal GFRP bar. That's why we are losing the loads here, and the constant axial load we applied like the 20% of the concrete strength, and the cross section area of the column also decreased suddenly because of the failure of the GFRP, longitudinal GFRP bars. So in all the columns, you can see these failures here. The hysteresis response of the GFRP reinforced concrete column showed a degradation, small degradation. So here we can see there is a small degradation when there is a due to the concrete deterioration, due to the concrete spalling, and later after this increases, the lateral load increased, reaching a second peak. Here I have attended a first peak in this column, but the lateral load increased and we reach a second peak, and this phenomena was different from the column with higher spacing of the transverse reinforcement. But in this case, our curve is completely straight, like a perfectly plastic, you can say, but it's not plastic. We can't say the plasticity in the GFRP reinforced concrete column. So which can be seen in the maximum lateral load capacities also. So here you can see the lateral load capacity attained by the 100 with 100 spacing of 100 millimeter was higher than the lateral load capacity attained by the column with spacing of 150 millimeter, and similarly for the drift. So with increase of the size of the GFRP spiral and cross type from number 4 to the number 5, it's so increase in both the lateral load. When we increase this part, number 4 GFRP, so the transverse reinforcement, I am increasing from number 4 to number 5. There is an increase in the lateral load as well as increase in the drift capacity of the GFRP reinforced concrete column. So now, in case of GFRP reinforced concrete column, because there is no ductility, because as I told you earlier, GFRP reinforced glass fiber reinforced polymer bars are linearly elastic until the failure. They does not show any elasticity. So that's why we calculate deformability index, which is different from the ductility. So deformability can be defined as the ability of the structure to sustain load without failure for a certain amount of deformation. And as we know that for the steel reinforced concrete column, we call it ductility, which is the ratio of the ultimate displacement to the yield displacement. But however, for GFRP reinforced concrete column, we don't have any yielding point. So because the GFRP bar doesn't yield. So in this case, what we have to do, we have to find a different way which shows the inelastic failure. Like in my concrete columns. So I have two materials, the GFRP bars and the concrete. And I know that the concrete can show inelasticity, not a bigger amount of elasticity, but they can show elasticity when there is a cracking, spalling of the concrete cover, or slippage of the bar also show some inelastic behavior. But generally those kind of thing when there is a dowel bar and the main reinforcement like lap splicing. So GFRP bar show inelastic behavior due to the deterioration of the concrete in compression. So therefore we selected the elastic displacement corresponding to the displacement at a concrete compressive strength of 3000 microstrain. So the ultimate displacement has been estimated for the experimental structure, and it can be based on the limiting the concrete compressive strength, peak load, like here, and small reduction in the peak load, like generally we'll take 80% reduction at this point, and first fracture of the transverse or longitudinal or any reinforcement. So for our case, where we can see here, so these two only can be valid for our case, for our columns. So that's why I selected the first fracture of the longitudinal bar as my ultimate displacement. So so that's why we can say the deformability index is the ratio of the ultimate displacement at the first fracture of the longitudinal bar to the elastic displacement corresponding to a concrete strain of 3000 microstrain. The influence of the deformability index on the studied parameter were the increasing the transverse reinforcement size increased the deformability index, and it was found that the lower spacing of the transverse reinforcement improved the deformability index, and increasing the longitudinal reinforcement ratio decreases the deformability index. So the energy dissipation can be defined as the area under the lateral load displacement loop for any given cycle I, and the cumulative displacement energy is the summation of all the energy up to n number of cycles. So the plotted result between the cumulative dissipated energy and drift ratio shows that almost the energy dissipation by all the columns, regardless of the different parameters, were almost same. There was no difference. Only the difference was like whoever is attending more drift, they are getting the more energy dissipation. Otherwise, it was almost same. So the comparing of the development of the longitudinal glass fiber reinforced polymer bar strain, the column with low longitudinal reinforcement ratio, this column, so it attended have high strength at each drift ratio, and which was reflected as the increased deformability index. So this is one of the reasons why we get the more deformability index in case of the column with lower longitudinal reinforcement. The longitudinal GFRP bar strain along the height spread more like is distributed, spread more in the column with low spacing of the transverse reinforcement, and which was consistent with the observed damaged region, because here we can see the damaged region is very high. Damaged region is very high compared to the columns with high spacing of the transverse reinforcement, and because the strain in the longitudinal GFRP bars were spreading above from like we can say my most damaged section is here, but it's spreading upwards. That's why it's continuously deteriorating the concrete cover above the position above this point. So the lateral GFRP reinforcement efficiently limited the lateral expansion of the concrete core, and this can be seen from the GFRP bar spiral and cross tie increased after load plateau. So after this point, we can see everywhere the strain in the GFRP spiral as well as in the GFRP cross tie were increasing. So which shows that it effectively confined the column core, which is now the lateral load prediction. The plane section analysis based on the assumption of CSA S806 and CSA S6 was used to predict the lateral load capacity, and CSA S806 design code does not consider any contribution of the longitudinal GFRP bars in compression, and whereas CSA S6, which is the highway bridge design code, recommended a compressive strength of the GFRP bars should be limited to a strength, compressive strength corresponding to a strain of 2000 microstrain. So, but however, in literature, it is reported from the coupon test that the compressive strength of GFRP bar is equal to 50% of its tensile strength. And from the present study, the tested column resulted also show the maximum strain of GFRP bars vary between 39 to 64% of the ultimate strength. So therefore, we consider a third strain, which was equal to the maximum compressive strain of the concrete according to the CSA S06, and which was equal to the 3500 microstrain. So the plotted axial load moment interaction curve. So the increase the GFRP bar compressive strength from 0 to 2000. Microsoft improved the axial load moment. It's improved the axial load moment curve. From here, it is the 0, where we use the compressive strength of GFRP bars to be 0, and here it is 2000 microstrain. However, when increased the GFRP bar compressive strength to 2000 to 3500 microstrain, the increase was negligible, and there was also no change below this point, below the 120 depth of neutral axis. There was no change. It was completely following the previous curve. And also the predictive lateral load was found to be conservative as compared to the experimental value, even when we consider the 2000 and 3500 microstrain in the glass fiber reinforced polymer bars. So therefore, the contribution of the transverse reinforcement was considered by using confined concrete model. So to develop this model, different amount of test was done to get the experimental values of the confined concrete and the normal concrete, and we just did a statistical analysis to predict a perfect a best fit to find this equation, and the confined concrete was calculated using this equation, and the confined compressive strain was calculated using this equation, and the lateral GFRP strain was limited to 6000 microstrain, which is required by the CSA S806. So the calculated confined compressive strength has an average value of around 45 megapascal compared to the 30 megapascal of the normal concrete. So the calculated lateral load capacity using the confined concrete model was almost comparable. It was around 217 compared to the 250 value. So it was nearby. So the GFRP reinforced concrete column could be suitable for the medium rise structures in low to moderate seismic zones. And the compressive behavior, because the compressive behavior of the glass fiber reinforced polymer bars in GFRP reinforced concrete column does not provide the plasticity required for the seismic response, and it makes it more likely to fail in a brittle mode under high loads. So therefore, the concrete columns with hybrid reinforcement consisting of longitudinal steel bar and transverse GFRP spiral and cross tie were tested. So here I replaced, so these 4 columns were replaced with a longitudinal grade 60 steel rebar, and keeping the rest of the parameter were same. The figure shows the casing of a hybrid reinforced concrete column with longitudinal steel bars and transverse glass fiber reinforced polymer reinforcement. So the failure progression of the hybrid, we call this column as a hybrid reinforced column because we are using 2 different materials, steel and glass fiber reinforced polymer. So the failure of progression of hybrid reinforced concrete column was almost similar to the GFRP reinforced concrete column, with development of flexural crack at equal to the spacing of the transverse reinforcement. The difference was the flexural crack in the hybrid reinforced concrete column develop up to 44% of the effective height of the column, and in case of the GFRP reinforced column, it developed up to the 70%. of GFRP reinforced concrete column. I will tell you the reason about this. I've already told you one of the reason, because the GFRP reinforced column spread the strain well, but in case of the steel reinforced concrete column, the strains are localized only near the plastic hinge zone. So the increase in the drift cycle caused splitting of the concrete corner concrete cover, and it was also earlier in the hybrid reinforced concrete column, because in case of the glass fiber, it was occurring at 1.4%, you can say, drift, but in case of this, it was like in some columns, it was below 1% drift. So which was followed by the concrete cover spalling, and this difference in the failure progression of the hybrid and the glass fiber reinforced polymer reinforced concrete column was due to, because in case of hybrid reinforced concrete column, the longitudinal steel strains along the column height were more localized than the strain developed in the longitudinal GFRP bars in case of the GFRP reinforced concrete column. So increased drift cycle caused deterioration of the concrete core, leaving the longitudinal steel bar unsafe. Between these two transverse reinforcement, and which lead to the buckling of all these steel bars in compression in all the columns, and which was earlier in the column with higher spacing, like 150, because the spacing is high, so they have like the concrete or cover, they have like large distance between these two stirrups, so that's why the occurring of the buckling was earlier in this case. And the failure of the first two columns was due to the fracture of the longitudinal steel bars, as we can see in this figure. And the failure of the third column was due to the buckling of all the columns, all the longitudinal steel bars, as can seen from this figure. All the longitudinal steel bars were buckled, and there was significant reduction in the lateral load also. And the fourth column failed due to the failure of the GFRP cross tie. The lateral strength in the hybrid reinforced concrete column increases until this point, which is the point of the concrete cover spalling, and after that it starts to degrade thereafter, and which this phenomena is completely opposite to what we observed in the glass fiber reinforced concrete column, where the lateral strength increased until the failure of the column. So due to the higher stiffness of the steel bar than the glass fiber reinforced polymer bar, the lateral load was more in the initial drift cycle, up to 1.5% drift cycle. It was higher in case of the steel reinforced concrete column, but after 1.5% drift cycle, it reversed the concrete cover deterioration, and more lateral load was absorbed in the GFRP reinforced concrete column. So now after this, you can see that there is a decrease in the lateral load capacity of the steel reinforced concrete column, whereas in each drift, the GFRP reinforced concrete column is getting more lateral load. So as explained earlier, the ductility was calculated as the ratio of the ultimate displacement to the yield displacement. So the ultimate displacement point was defined at the 80% peak point. This point, 80% of peak load at the post-peak stage. The yield displacement point from the experiment can be defined as the first yielding. This one is the first yielding. Like the first yielding means when we reach the 2000 microstrain in the longitudinal steel bar. However, to make the comparison to the present column with conventional steel reinforced concrete column, the yield displacement was computed by equating the area under the experimental curve to the equivalent elastic plastic bilinear curve, and the drift capacity was around 80% of the peak load at the post-peak stage. The effect, there was negligible. So there was negligible change in the lateral load capacity when increasing the spacing of the reinforcement. As we can see in the when we increase the spacing from 100 to 150, the lateral load increase was not that much. It was more or less same, but it affected the drip capacity and the ductility of the column. Increasing the longitudinal bar ratio increase the lateral load capacity, but it reduces the ductility index of the hybrid reinforced concrete column. However, all the columns achieved a drip ratio of 2.5% or more, which is allowed in the North American design codes for normal importance building. The strain developed in the longitudinal steel bar at two level, like 50 millimeter above the column stub interface and 350 millimeter and 150 millimeter below the column stub interface were plotted here, which is shown here. The strain in the longitudinal steel bar at 50 millimeter above the column stub interface saw a jump in the strain. So a jump in the strain after the yielding of the steel bar, and at 2.0 at 2% drift ratio, the strain hardening caused strain to redistribute. The strain gauge installed at 150 millimeter below the column stub interface recorded strain lower than the yield strain, like 2000 microstrain, which showed that the development length which was provided for the column steel bar, longitudinal steel bar, was adequate. And the observed phenomena was similar to the observation in the past research for the concrete column confined with the steel ties. So therefore, we can say that the behavior of the longitudinal steel bar was unaffected by the type of reinforcement, transverse reinforcement used, either steel or GFRP stirrups. The GFRP spiral and cross tie effectively confined the concrete column after the yielding of the longitudinal steel bar, which is showed as the non-zero strain at the zero drift in both spiral and cross tie. And the development of the significant strain in the GFRP spiral and cross tie at the steel bar buckling. At this point, there is a large amount of strain developed. So this the confinement effectiveness of the steel ties beyond yield strain of 2000 microstrain was found to be insufficient, whereas the strain developed in the GFRP, generally in the GFRP spiral and cross tie, went beyond 2000 microstrain and provide effective confinement until the failure of the column. So as I already told, how we calculate the dissipated energy dissipation and the cumulative energy dissipation. So the cumulative dissipated energy in the hybrid reinforced concrete column was much high. I am comparing between the hybrid reinforced concrete column and the GFRP reinforced concrete column. So in case of the hybrid reinforced concrete column, which it was much higher than the GFRP reinforced concrete column, and you can see that at a 1.5% drift ratio, the change in the cumulative dissipated energy was almost twice more than the preceding drift ratio, 1%. Here it was 38, and here we are getting around 70 or 80%. So after 1.5% drift ratio, the hybrid reinforced concrete column so significant plastic deformation, and this was due to the significant plastic induced by the severe concrete deterioration and steel bar buckling, and which is observed as a large residual deformation here. But whereas in case of the GFRP reinforced concrete column, the inelastic behavior was only induced by the concrete damage, and the descending part of the lateral load displacement curve approximately approaches the zero, and it reduces the area under the lateral load drift ratio curve. Therefore, the GFRP reinforced concrete column experience lower cumulative dissipated energy than the corresponding hybrid reinforced concrete column. The stiffness degradation of ith cycle was calculated as the sum of the peak load, these two load, and which was divided by the corresponding displacement. So the decay The decay in the stiffness was more rapid at the initial drift cycle due to the development and widening of the cracks and the concrete degradation. And after the 1% drift ratio, the stiffness in the hybrid reinforced concrete column decreased due to the yielding of the steel bar and continue to be lower until the end of the test. The stiffness degradation was gradual in both type of column, either GFRP or hybrid reinforced concrete column, after the 2.5% drift ratio, and this was because of the crack stabilization. So in conclusion, the hybrid reinforced concrete column consisting of longitudinal steel and combined with GFR, glass fiber reinforced polymer spiral and cross tie, showed stable behavior, achieving around more than 4% drift ratio, which were the well-confined hybrid reinforced concrete column. So therefore, we can say that concrete columns with hybrid reinforcement could be reviewed as being acceptable material for use in new construction for high earthquake hazard zones. The strain developed in longitudinal steel bar, so it was unaffected by the type of the reinforcement, transverse reinforcement used. The glass fiber reinforced polymer cross tie effectively confined the hybrid reinforced concrete column after the yielding of the longitudinal steel, and GFR, glass fiber reinforced polymer spiral, become more effective in confining the column column core after concrete covers falling. And in hybrid reinforced concrete column, the drift capacity decreases as the pitch of the transverse reinforcement increases without affecting the lateral load capacity. As seen from the failure progression of the glass fiber reinforced polymer and hybrid reinforced concrete columns, the failure progression of the GFRP reinforced concrete column was more gradual than the hybrid reinforced concrete column. The longitudinal steel bar in hybrid reinforced concrete column induces plasticity, which increases its cumulative dissipated energy compared to the GFRP reinforced concrete column. The stiffness degradation of the hybrid reinforced concrete column was lower at 1% drift ratio than the GFRP reinforced concrete column, and continued to be lower until the column's failure. And finally, the compressive behavior of the GFRP bar doesn't provide any elasticity required for the seismic response in high seismic zones, whereas steel bars in hybrid reinforced concrete column give resilience to the column in compression part and make it more suitable for the high seismic zones. So currently I am working on the lab splicing of the longitudinal bars on the behavior of GFRP reinforced concrete column, and in addition to that, I am also working on the behavior of concrete column reinforced with hybrid longitudinal reinforcement. Here in the longitudinal reinforcement, I am using both GFRP and steel, and I am seeing how much percentage of steel should be required to get an adequate seismic response. So for this project, one of the students from IIT Hyderabad is helping me and further we are extending this project to use different types of concrete. Like in present day, we can get plastic concrete from there we can get a plasticity, so which will be helpful to get the required deformability, or you can say the plasticity from the concrete. And the GFRP bars are very good for the corrosion resistance, so it can improve the service life of the structure. So in future, the impact of the different concrete types like fiber reinforced concrete or high strength concrete should be investigated, and also the feasibility of different types of fiber reinforced polymer bars. Like recently, basalt fiber reinforced polymers bars are tested. It is in the material phase, but also they are doing in the structural phase. It should be examined. So thank you for your kind attention.
Thank you so much, Dr. Girish, for such a descriptive and knowledgeable presentation. And it was purely research-based presentation. I hope that all our audience, which are almost working in they are the research students somehow. So this must have inspired almost all our audience, as it was too much inspiring and purely research-based.